Okay, this is part 2 of Unit 1F. So this is a z-score, kind of a blank, generic, normal curve for z-score. You can see that 0 is the mean. It's in the middle there because it's symmetric. So the mean and median are going to be about the same in the middle there. You can see that we go 3 standard deviations to the right. Those are all positive, and then 3 standard deviations to the left. Those are all negative. When you're doing z-scores, you're measuring in standard deviations. That's the unit of measure. So standard deviation is just 1 for that generic graph. We'd like to be able to graph that one. To standardize, simplify the z-score. So we can use the z-score equation. We learned that the other day. So if you want to write that down again, you got it. But it's the value minus the mean divided by the standard deviation to find the z-score. Okay, so for this one, because all normal distributions are the same when we standardize scores, we can find areas under the normal curve. So this is something we find quite often in stats. Fortunately, we don't have to do that by hand. That looks like it would be complicated to do by hand to find an area under the curve. In calculus, they do things like that. The distribution for ITBS scores is approximately normal, which is what we want to see. If we can't use this technique unless it's approximately normal. So a mean of 6.84, you can see in the middle there is 6.84, and they went by tick marks increasing by and decreasing by 1.55. So they added and subtracted. Again, the way you do that in your calculator is you type in 6.84, press enter, hit plus 1.55, which is standard deviation, hit enter a couple more times, and it'll just repeat that answer plus that. That gives you the positive terms there, and then if you type the number again, then hit minus 1.55 and press enter a couple more times, it gives you the lower bound values there. Just really quick way of getting those numbers, plotting them on your graph. That hopefully is almost automatic. So if we want to find the area of the curve, it looks like 6 or less. Get out your calculator, hit the menu key, go to stats, and it's under distributions, number 5. And so it's a second choice. So menu 652 is one way to get there. So hit norm CDF. We're going to norm CDF that bad boy. So I usually, the default is negative infinity, and you can see on the left, it's going forever to the left. So we're going to leave it that, hit tab. The upper bound looks to be 6. Well, I'm going to do it two ways. First, let's figure out the z-score. Let's do it with the z-score. So find the z-score. So you would plug that into your calculator. 6 is the value minus, they said 6.84 is the mean, and they said standard deviation is 1.55. So you get that z value of negative 0.542. And you can see that line, that purple area kind of starts kind of halfway between 0 and negative 1 on the scale. So negative 0.542. So we can use that to when we do our z-score equation. So it looks like it's going from a lower bound, the interval is shaded there, from a lower bound of negative infinity all the way up to negative 0.542. I'm going to leave the default of mean of 0 and standard deviation of 1 because that's true for z-scores, and that's what we're using. And we get 0.293909. Perfect. By the way, I'm emphasizing this because I want you to get in the habit of doing this. So on the actual test, if this was your problem and you were doing the work here, what I want you to do is write out the command as your work. It's okay to have, say, I did this in my calculator. So norm CDF, and it's fine to put these numbers, negative infinity, negative 0.542, comma 0, comma 1. But below it or above it or something, you need to put what that terms mean. So that's lower. This is upper part of the interval. This is the mean for z-scores. And this is the standard deviation. And so if you put that on your test, that is good enough for us to know you know what you're talking about. If you only put the calculator command and don't put what those variables are you typed in, sometimes you lose a lot of points. So definitely worth your while. I've seen it where you get full credit if you have that, and it went from a 4 to a 2 just by not having the what those things mean. So I would definitely show your work on that one by writing the names of the variables you typed in the norm CDF. So you can actually do this a different way. We converted to z-score first, but we could have ignored z-score and just solved this with norm CDF. Let's see how that would work. Menu, 652, lower bound. I'm looking at the graph there in the bottom right. No, bottom left, sorry, bottom left graph. So lower bound still negative infinity. I mean, a tab looks like 2.19. Let's see, no, it goes all the way to 6, right? So it goes to 6. Not, so last time we gave the z-score where 6 is at. So we used z-score last time so we could default the last two to 0 and 1. If I use the number 6 here, I've got to use the actual mean and standard deviation given to us for the problem. So 6.84 and 1.55. Get the exact same answer, basically. I rounded off the z-score, that's why that's slightly different. Technically, the second one would be a little bit more accurate, but both answers are just fine. Again, you would show your work when you use calculator speak, all that. And in words, 29.46% of the values are less than 6. They require z-score rounded to 2 decimal places. I hadn't heard that before, but I think that's probably about right. So we've done all that. We've done all that. Okay. So to find the areas, you draw it. Always a good idea to draw it and shade appropriately. Perform the calculations. In almost every case, it's going to be using norm CDF on your calculator. So the answer to the question was asked. That's what I just told you about the fact that they want you to label what those variables are. Don't just write negative 1006, negative infinity, comma 6, comma so forth. But just, write out the variables for those. Suppose that for one model of car traveling at 62 miles per hour under typical conditions on drive pavement, the mean stopping distance is 155 with a standard deviation of 3. The mean stopping distance follows a normal distribution. What I would do first, if I were you, is draw this guy, right? So, and this was easy to do even without a calculator, really. So 155 is in the middle. That's the mean. It's symmetric. You go 3 standard deviation, 3 to the left, so that's 152. 3 to the left of that is 149. 3 to the left of that. So there's typically we go 3 standard deviations, what we'd like to do in each direction. Then we go 3 to the right, so 158. 3 more to the right, 161. 3 more to the right, 160. Okay, so suppose one car is traveling at 62. Mean stopping distance is that. About what percent of cars take less than 160 feet to make an emergency stop? So if you have your graph, you're thinking, okay, less than 160. 160 is right in here, right? That's 160. So you're kind of thinking there, and you're shading to the left, so less than that. So stopping distance left. So a lot of cars have that, and it's going to be shaded to the left. Let's see what they did. Yeah, they drew it a little nicer than I did, and they shaded left. And so now you can do your norm CDF at this point. So go menu 652. Lower bounds, negative infinity, goes to left forever. Upper bounds, if you want to do it this way, it's 160. Whoops. So negative infinity. So negative, you hit the pi key at the bottom there. And choose infinity. So negative infinity to 160. and then the mean was 155, standard deviation was 3. Get that. If I had converted to z-scores, so 160 z equals minus the mean of 155 divided by standard deviation of 3 ends up being 5 over 3, which is 1.666. Repeating. So go at least 2 digits to 1.67 would be fine there if you want to round to that, or truncate it. So let's use the z-score of 1.66 and see if we get the same answer here. So norm CDF this guy, so menu 652, negative infinity to, we think, 160, with a mean of 155, standard deviation of 3. And we get the same answer we got just a minute ago. So just different ways. Both ways are fine. You need to know how to do Z, even if you don't do it all the time, it will pop up. You need to know Z, so it's not bad practice to do the other way, but it's kind of up to you, actually. Show your work. That's what we did. Okay, so I think Nellie is actually a pretty long hitter with the driver. So let's see what it says. Okay, when Nellie hits her driver, the ball travels on a normal, can be modeled by a normal distribution with a mean of 274 yards and a standard deviation of 8. So it's not one drive. We're talking about if you take all of her drives and plot the distances, they actually form a normal model. How likely is she to drive longer than 260 yards? So if you scale it out, so again, you want to start with kind of a blank normal curve, put 274 in the middle, add 8, subtract 8 3 times, basically. And you'll have the scale down there. So you can see the scale, distance traveled by her, one of her many golf balls she hits. So the question is, how likely is she to have a drive longer than 260 yards? We want to find the area under the curve. By the way, this might help you understand something. The area under the curve is 1. The total area under the whole curve, shaded and unshaded there. So if we find the percentage that's shaded there, we'll find the chance or the probability that she hits it longer than 270. Unlike math class, it doesn't really matter if the question is equal to 260 or longer or just greater than 260. They're the same question for this type of question. So it doesn't really matter the phraseology of that. You could find the z-score first, plug it in, given the information there, you get negative 1.75. So 160 would be a bad drive for her. It's almost 2 standard deviations below the mean for her typical drive. Using technology, so you could do CDF, again, menu 652. You would want to label what those are, lower bound, upper bound, mean, standard deviation, but that's using the z-score. So if you use z-score, you can leave the default to 0, 1 for the mean and standard deviation there. If you don't standardize first, if you don't get the z-score at all, you can just plug in the numbers given. So we want to get from 260 to, I would say it differently. I would do to infinity here. So if I were doing this problem, I would say menu 652. Lower bound is 260. The shading starts to the left at 260, but the upper bound, I would call it infinity. I would not limit it to 1,000, although I don't think it's going to make a difference, honestly. I think it's a better idea. Just going to the right forever, put infinity. The mean, I think, was given in the problem. It was 274. Standard deviation was 8. And you get 0.959941. That looks about right. And so it didn't make a difference there. About 96% of Nellie's drive travel at least 250 yards. Pretty impressive, right? So that she goes, actually 260, not 290. I don't know where the number came from. It should be 260. Okay. There are actually we're going to say two methods because we don't use the table. I don't recommend it. We only use the calculator, but there's two different methods to get this calculator. So what percent of the values lie between 6 and 9? So you could find the z-scores for both of those, right? So if you go to the trouble of finding the z-scores for both of them, now I'll use z-scores for that. So menu 652, lower bound seems to go from negative 0.542, and upper bound is 1.394. Leave the default 0, 1. So nice by that, you get a little work of the work front end, but it just does it for you, 0.6244. Again, you want to label those values, you want to write them on your paper, what the variables are. And so you get that same answer. If you wanted to do it, the same question with the mean and standard deviation given in the problem, so then you use 6 to 9, instead of the z-scores, you get the same answer. So I kind of prefer that way. 62% of Indiana, your Indiana 7th graders earn the equivalent ITBS vocabulary scores between 6 and 9. Okay, how likely is she to hit a drive between 275 and 295? So again, not a bad idea to draw it. You're kind of shading from 275, just over the mean, to 295, which is pretty far out there, pretty close to 2 standard deviations there. You could use technology without standardizing, without getting z-scores. I probably do that usually. About 45% of Nellie's drives are between 275 and 295. Okay, that's the lesson. Let's just kind of work a few of these problems so you're ready. Okay, so for businesses trying to sell products online, one important number is the web page load time. If web page doesn't load quickly, viewers are more likely to become impatient and leave the web page without making a purchase. That's 100% true for me. Page load time for Target.com, a laptop at Mr. Tyson's house has a mean of 2.53, a standard deviation of 0.26. I would, so because it says, let's say it's normal. Load time. So they should have said in the question, data is approximately normal. They didn't say that, but because the section we're in, I know it must have been approximately normal, I think. So see what they say. But I think they meant to say that. 2.53 would be in the middle. Then you can add 0.26 to that 3 times. Subtract 0.26 to that 3 times. The way I like to do that is type in 2.53. Press enter, hit plus 0.26. Press enter 2 more times. So 2.79, 3.05. Always go 3 standard deviations inside. 3.31. And then again, type in 2.53 minus 0.26. Hit enter a couple more times. 2.27, 2.01, and 1.75. Oops, sorry. So about what percentage does it load in less than 2 seconds? So less than 2 seconds, so you want to go, okay, 2 is like, oh man, right over here is 2. So kind of shading here and to the left. All that is shaded just to the left of, not 2.01, but 2, right, just to the left of that. So that's your picture. Then you get your calculator out and do the norm CDF for that guy. So menu 652. I'm going to say negative infinity to, I don't love using z-scores. I'd rather do it this way. It just seems faster. And then 2.53. If I want to know how to do those, you have to do it every time. Okay, so we get, wow, 0. If we mouse up there and press enter, it'll show me there's no more digits. So 2.53. think I typed something wrong. This should be 2.53. I think that's right. Okay, so 0.0207. So a little over 2% of the time. 0.0207, yeah, so we got it. About 2% of the time would be the answer. The Center for Education Statistics recently collected data on 1 year's math scores on the SAT. The scores are approximately normal distribution, that's what I wanted to see in the last question, with a mean of 533 and a standard deviation of 100. Getting scores 650 or more is very good. What percentage of students took the SAT? So try this one on your own, stop the video, try it. When you do it, if you get your answer, it should look like this. 650 will be shaded to the right there. Use technology. Notice they put embedded what the variables are right in the statement there. So I'm fine with that. Some people put it below, before, after, above. And the answer is 12.1% of the areas to the right of that. And again, you could have used z-scores. So that was the first way, or not use z-scores and put in the actual mean and standard deviations there. You still get 12.1%, or 12% essentially. So try this one if you want more practice. That's what the answer is. And you got it. That's your lesson for today.